Good afternoon, everyone. My name is Christopher Minjares, and I'm going to be talking about the wire embedding device for large area additive manufacturing system simulation, which is the final project for computational mechanics class with Dr. Stewart. So let's begin. The main objective of this project is to simulate the wire embedding process using ANSYS 2019. This study will provide better understanding of the reaction forces as well as the deformation due to the heating on the copper wire, which is going to be heated at 230 degrees Celsius and will be interacting with the substrate as it can be observed on the image below. The wire embedding technology basically is able to place copper wire within a plastic substrate. This technology is currently only working with plastics. So we're trying to bring that technology to a big area additive manufacturing system, which is commonly known as BAM. Having this technology in a larger system, which compared to a desktop printer, which has a volume of 0.3 millimeter cube, where in the BAM you have a 18 millimeter cube in built volume. So this is making it attractive to have this technology within the system. Now, the heating method needed to be able to melt the substrate and then place the wire within the part needs to be really high. That's why we need a heating method which is capable to give us 230 degrees Celsius in a small amount of time. So in this case, the copper wire is going to be fed at high rates. That's why we needed this type of heating source. And the gauge of the wire is going to be 14 copper gauge wire, which is going to be embedded in these big parts. So in this slide, you can observe the tool that we developed at the WM Center, which is able to place the wire into the substrate being printed on BAM. So right here we started with the spool of wire, which again is a 14 gauge copper wire. Then we have this little guide which has a B groove B groove which is able to guide the copper wire. Then we have the wire straightener, which are a set of bearings which are going to be correcting the bad portions of the copper wire. Then we have our driving roller, which is going to be connected to a motor and at the same time is going to be pulling the wire. Now right before the application roller, we're going to have the torch, which is going to be heating our copper wire to a set temperature, which is 230 degrees Celsius. And at the end of the travel, we're going to have the application roller compressing the copper wire against the substrate. Therefore, it's going to be able to embed the wire. So for the engineering materials which are going to be needed in ANSYS 2019, we're going to use copper alloy, which is commonly used for the fabrication of copper wires. Then we're going to be using aluminum, since our application roller for the tool is made out of aluminum. Then the material of the substrate, it's ABS 20% glass filled. The values of elastic modulus, Poisson's ratio, and the UTS were pulled out of our research being done at the Keck Center as well. So these are the material properties that were obtained by pulling these tensile bars. The source is right there, so I won't be talking too much about it, but these are the numbers I used for each property of the material within ANSYS. So this is the geometry that's going to be used for the simulations on ANSYS. This is the geometry done in Design Modeler. So right before two slides before, we were looking at the actual tool that's gonna be able to embed the wire. We were looking at it from the side. Now we're looking at it from the front, where we have our compression roller, then our 14 gauge copper wire, and then our ABS 20% glass filled substrate. And all these units are in millimeters. I want to add that these dimensions were taken from the actual design of the tool, so this is real, and for the substrate is an arbitrary number just to show the interaction between the copper wire and the actual substrate while it's embedding. After getting the geometry on Design Modeler, now we move uh, to the model portion, which is the mechanical setup. So where I assigned a specific material for each individual component. Again, for the roller was aluminum, for the copper wire was copper alloy, and then for the 20% ABS glass field, I had to create a new material where I added the properties that I showed from the paper. So now, after doing that, we just go ahead and do the contact regions, which I had the frictional contact regions first between the ABS and the copper wire, where I add the friction coefficient of zero 0.4. This value I got it from Sarin et al. 2018, and then I added the frictional contact as well between the copper wire and the aluminum roller, which the friction coefficient is 0.1. So I got that value from Liu et al. 1964. So for the boundary conditions, I did a steady state thermal analysis first to determine the actual temperature of the components when they were exposed to the copper wire at 230 degrees Celsius. With this study, my goal was to determine how much heat we're transferring to the roller or to the substrate, then determine which one we're taking most of the heat. And if it comes out that the roller is taking most of the heat, then it will be a good idea to insulate that portion of our tool. And then the temperature for the substrate is gonna be 80 degrees because right after printing the material is still hot, then we're thinking on embedding. That's the process. So that's why it's set to 80 degrees Celsius, which that value we have seen it using IR imaging, but again it's just for modeling purposes. So these are my boundary conditions for the model. Then after doing the steady state thermal analysis, I went ahead and added the static structural analysis, which now it's gonna help me determine the deformation of the substrate. So right on A, it says imported body temperature, which is gonna be taken from the previous study. Then I added fixed support at the bottom of the substrate, frictionless support on the side of the application roller to avoid any movement on the X axis. Then I added a thermal load of 230 degrees Celsius, which is again for the copper wire. Then I added these displacement 2 and 3, which were used to avoid any displacement on the X direction, but also they're free on the Y axis. So that will give you the deformation. So then for the mesh, I have a lot of trouble trying to do a fine mesh, which were able to run the simulation properly. Usually I was getting the error of limitation of elements. So then I have to be playing actually with the resolution, the adaptive, and the element size. So at the end, I went ahead and did an element size of 0.4 millimeters, and I used the adaptive sizing, and then the resolution of 5. This was for the entire geometry. And then for the contact areas, uh, I actually used the edge sizing function, which were applied on the contact again. That was made for more accuracy on each individual study. So on this one, I did an element size of 0.1 millimeters, and this gave me a total of 17,969 nodes and 5,802 elements. The limitation on the student's license is 32,000, so I was below, but still, if I added a bunch of more fine measures, it will be a limitation on my simulation. Now for the results, there's gonna be three major outputs. One's gonna be temperature. That will help us to understand the temperature, if it's being transferred more to the ABS or to the aluminum compression roller. And if so, we're gonna need to insulate the roller to guide most of the temperature to the ABS substrate and have better quality embedding. Also, we're gonna have deformation, which the actual deformation happening on the substrate while embedding the desired displacement of the wire within the substrate is gonna be 0.814 millimeters, which is half of the diameter of the copper wire. And then the force reaction, which will have to determine how much force is going to be needed to apply into the wire on the y direction to be able to obtain that desired displacement. Now, after the boundary conditions, the mesh, the contact regions, the geometry, and all that, now we have actual results from the simulation. The first one is temperature, taken from the steady state thermal simulation, where we can observe the copper wire being heated at 230 degrees Celsius. And then the actual results are showing that most of the temperature is going to the aluminum compression roller. We can have 137 degrees, while in the substrate the major portion has 91 degrees Celsius. So most of the temperature is going to the aluminum application roller, which in the case of embedding, it will be good if we have all that heat transfer going to the substrate for it to be able to melt, then placing the wire while pressing against the substrate. So this will facilitate the embedding a lot and will have a better quality embedding. Now, after having the results for the steady state thermal simulation, I went ahead and basically ANSYS within my study is taking the previous results from the thermal analysis, and it's transferring those results to the static simulation. So right now, after all my boundaries that I mentioned before, where the actual displacement of the wire within the substrate is 0.8162 millimeters, which the set displacement was 0.814 millimeters. So I'm assuming that increasing temperature, it's making the substrate to expand, and therefore the displacement is higher than the set displacement and the boundary conditions. After that, we're gonna have the output on the y-axis deformation, which again, the previous one was the total deformation. Now on this one, we're having a 0.816 millimeters in the y displacement as a maximum. That means that the roller did displace that, but actually the substrate is not experiencing the same as the copper wire and the roller. So uh, from visually, what can we see is less than that, uh, and this is due to the material properties of the actual ABS 20% glass field. So I'm assuming that we will need a higher temperature on the copper wire, or maybe more force applied on the wire. So the next one is gonna be the x-axis deformation. So for the x-axis, we don't have too much deformation. Basically, it's 0.0002 millimeters the maximum displacement on the x-axis, and this is happening on the application roller. So I'm assuming that we're getting a little bit of displacement on the x. It's so small that I don't think we'll have to worry too much about it. But then we're having some on the x direction, so that might be uh, a little bit of concern, but I don't think so since it's too small. So our next output from the simulation, it's the reaction force on the substrate after the displacing the roller and the wire. We're having a reaction force of 17,598 newtons, which is I don't think it's very accurate, the result. I will have to do a further study on the reaction force, since I think it's too big. And for sure the thermal expansion and the application roller has springs on top are helping with the placing of the copper wire, but I think that those 17,000 newtons, it's too much. So I'm assuming something's not correct. Therefore, we'll need further analysis on the reaction force for this case. So in conclusion, the substrate will experience less temperature than the actual temperature of the wire. The melting point of the ABS glass field is 215 degrees Celsius, and since the copper is at 230, um, it has to contribute to deform the material easier. Again, from the results, we observed that the aluminum roller was taking more of the heat than the ABS, so a possible solution to that will be insulating the aluminum application roller to have better heat transfer to the substrate. The deformation of the material is actually higher than the set displacement, and I assume these to the thermal expansion of the material due to temperature, which the copper wires having and then transferring it to the substrate. So that helps a lot. Looking at that, the actual heat is helping deforming the substrate. And then again, for the force reaction on the simulation was 17,000 Newton, which again will require further analysis, since I don't think the tool is experiencing 17,000 newtons. Again, this is my my suggestion, but it might be correct too. So we'll have to determine more, probably using instead of the set displacement, probably we can use the strength of the springs having them displace some distance so we can get better results on the simulation. And these are my sources that I used for obtaining the values for the engineering material, the frictional coefficients, and the actual motivation for this simulation. Thank you very much, and if you have any questions, let me know so I can answering them. Thank you.